Alright, welcome back to my channel, and welcome back to another AP Pre-Calculus video. In this video, we'll be going over topic 2.2 of Unit 2 in AP Pre-Calculus, and it goes over changing linear and exponential functions and how they are related to arithmetic sequences and geometric sequences. Hopefully you went over 2.1 already, and in that we learned that arithmetic sequences behave like linear functions, and that geometric sequences behave like exponential functions. And then from knowing that, we can look at these two tables right here, and it kind of shows the similarities with in linear sequences. I don't know why it's changing, but yeah, so we can see here that this one right here is similar to the slope-intercept form. So B is kind of like the initial, and it is because when you think about it, B is the y-intercept, and the y-intercept has x is equal to 0. So it's kind of like the initial one. It's the 0th term. And then the other equation is like the point slope form. And then when we look at geometric sequences and exponential functions, we see that the equation that with the initial, or the first equation, similar to a regular exponential function right here. Looks like that. Or you can say this and using r instead of b, but no, they're both just like the common ratio, or what it's like increasing or decreasing by. And then this is the other equation is similar to this. So that's just like a table seeing the connections closer, since 2.2 talks about linear and exponential functions and not just the sequences. And so this talks more about linear functions and exponential functions by itself. So we know linear changes by a constant rate, and so does arithmetic sequences. Arithmetic is the variable d, that's their difference, common difference, which has to be the same every time, while geometric is r, common ratio, and a ratio is the same, but it's like being multiplied instead of added. So that's why it's similar to that. Exponential is changed proportionally. So linear functions is based on addition, which basically means it could also be subtraction, multiplication here. When you divide by 2, it's also just the same as multiplying by like 1/2. That's, for example, if you're thinking it could also be division. And then down here it says if you have 2 points, you can write the equation of a linear function, exponential function, arithmetic sequence, or a geometric sequence based on all of these. And basically for the sequences, the number term, so say like the second term is equal to 50, 2 would be the x and 50 would be the y, because like, just gonna give an example, an arithmetic sequence that's equal to 50. We know that 2 is equal to n, so that means, and n is basically the x value, because when we look at this right here, we see that they're in the same spot. So 2 would be the n, and 50 would be the y. Now we're on to example 1. Selected values of several functions are given in the table below. For each table, determine if the function could be linear, exponential, or neither, and give a reason for your answer. So we just look at all of these. All of these should have equal length intervals. As we can see here, this goes up by 3 each time, and we're only talking about the x values. This goes up by 1, this goes up by 2, and this goes up by 5. We see that those are equal length, but that doesn't matter because they should all be if we're trying to answer this question. So basically what we're trying to see is what kind of function this is. Or it could be neither. If it doesn't show a constant rate, or it doesn't change proportionally, change by a common ratio. So the first one, a, we see at first it minuses 2, minuses 2 again, minuses 2, and then minuses 2. So we can see it is linear. And with these kinds of questions, it just gives your reason for your answer. So we would write kind of like a sentence or two, basically saying how over equal length input value intervals, which is the intervals of the x value, we see that the output values of this function, which this one is f of x, changes at a constant rate, which is why it's linear. And so if we're saying it's exponential, then we would say it changes proportionally. If it's neither, then we would say because it does not change at a constant rate, or nor does it change at a proportional rate or proportionally. Yeah, I'm just saying that because I'm just not going to write that. So let's move on to the next one. This one +1 at first, then +3, then +5, and then that looks like a times, +7. And so we know that's not correct. This is all different. But if we do see it does +2 on the next go, aka meaning that it's quadratic and not linear or exponential, so it's neither. And like we said earlier, when it's neither, basically all of these answers are kind of similar, but you're just saying a different reason at the end and saying how the output values are not changing at a constant rate or changing proportionally. So h of x, we see this is +1. Oh, but this is +2 and this is +4. That's +8. So that means that it's multiplying by 2 times 2 times 2 times 2. So that means it's exponential. And the reason for that is because it's changing proportionally. Now the next one. So d, it looks like each of them is multiplying by 1/2, aka dividing by 2. So that is changing proportionally, changed by a common ratio, so it's exponential too. And for an exponential or linear, I think in your answer would be better if you're saying by like what constant rate or what a common ratio, like it's changing at a common ratio of 1/2. You would say it's changing by a constant rate of -2, and so on, because who knows, your teacher might minus points for you not saying what is the output value, how is the output value changing, by what, not just what function it is. So now on to example number 2. I'm going to read the question, but you can skip it. A wild rumor is spreading that Mr. Passwater won 3rd place in the World's Strongest Man contest. Mr. Passwater definitely probably didn't start the rumor. The number of people that have heard the rumor can be modeled by using a geometric sequence, so that's important. Where 43 people had heard the rumor on day 3, and 140 people have heard the rumor on day 6, so 43 goes with day 3, so I'm going to change the color. 43 people day 3, and 140 people on day 6, and so now we're trying to find according to the model, how many people to the nearest whole number have heard the rumor by day 10. So we're trying to find what is a number on day 10. So that means, so the days seems like the number in the sequence, or the number term. So we can write this here. It's geometric, so we're using G. We can write using a table here. I think a table is recommended here. So because as we said earlier, n is equal to x, so instead of x and y, we're going to write n here, and then we know we're using geometric, so I'm going to write g of n, so g of this whole thing is equal to that number, and we're going to get 3 rows here, because there's 3, the third one we're trying to find here. So the first one is 43 people, and that would be the g of n, and then day 3, because that's like the third term. And then day 6 is 140 people. And then by day 10, we don't know that, but we know that's the 10th term. And then we can just put it like a question mark there, because that's what we're trying to solve. And so we have 2 points, and we're trying to solve for the y of the last one. We don't have the initial one on the initial day, how many people heard the rumor. So we're going to be using the equation without the g of 0. So yeah, that's multiplied by r to the power of n minus k. So n is basically just one of the terms, and k is also one of the terms, so 2 of the terms, but I believe that gn has to be the term number greater than g of k, because when you're subtracting here, it probably recommended that it's 6 minus 3 rather than 3 minus 6 when we're talking about this equation. So when we replace it, g of n, so we're going to use g of 6 is equal to g of 3 times r. That's what we're going to be trying to solve here. We don't know that. 6 minus 3. And so we can replace these numbers right here with what they equal to here. So g of 6 is equal to 40. Oh, not 43. 140. 140 is equal to 43 r to the power of 3. Since we subtracted this here is equal to 3. So that's 3. Now we can divide this by 43. And then we can see here, this equals to this. So we can cube root each side. That takes away the cube, and then we cube that number. So r is equal to the cube root of 140 over 43. And we don't know that. We can put that into the calculator later in the next one. So now, moving on. Now that we know the r, we can replace the r in this equation and then put g of n is equal to g of 10 because we're trying to solve for that. And g of k can probably be this one or this one. But I'm going to use g of 3 because it's a lower number, so it's probably easier. So g of 10, what we're solving for, with g of 3, and we can put 43 because that's what it is and we know it. Cube root of 140 over 43. We don't have it simplified, but we can just put into the calculator. And then 10 minus 3, n minus k. So g of 10 is equal to 43, this number, to the power of 7, that right there. And then we simply just do that into the calculator. We're going to do that here. So just clear that. So 43, parentheses, we click math to get the cube root here. Or we can use 5 right there to get any number. But since 3 is already there, we can do that. And then 140 divided by 43, arrow, parentheses, to the power of 7. And that gives us that number. We can write that g of 10 is equal to 675.576. And when we look back at the question, quite messy here, I'm going to erase this circle. It says how many people to the nearest whole number. So the nearest whole number for this number is going to be 676 because this is 5. And that rounds up to 6. And so 676 people by day 10. So now moving on to example 3. A large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. So let's underline that. If the 5th row has 31 seats and the 11th row has 49 seats, determine how many seats there are in the 25th row. So that's quite the jump there. So let's underline these numbers. Let's use this color right here. Seems kind of cool. 5th row, 31 seats. Oh, that's actually kind of cool. It does that. And then the 11th row has 49 seats. So let's draw our table. You don't have to draw a table. You can simply just write G5 or A5, is equal to 31. It might be quicker. But for here, we're going to use the table to simply show it better so you guys can see it. You can write X and Y, I guess. Or you can write rows and seats, but yeah. And this is A because we're doing arithmetic sequence. So the 3 points. First one is the 5th row is 31. Alright, I'll write it into the color. 31. And then the 25th row, which is what we're trying to solve for. So question mark it or put a variable or whatever. So this is arithmetic sequence. Arithmetic. So this is an arithmetic sequence, so we're going to be using one of the arithmetic equations, but we're not going to be using the one with initial because we don't have initial, so we're going to be using the one that has AK, so AN is equal to AK plus D N minus K. So we always know that N goes before K, and when we're using N and K, the number in the parentheses, talking about both types of sequences, would be N minus K. And then when it's the initial, the number in the parentheses will only be N. So replacing these, AN is going to be A11. A11 is equal to A5 plus D, which we're trying to solve for. And then N, which is 11, minus K, which is 5. So we can replace the A11 and A5 because we know those. The 11th term is equal to 49. The 5th term is equal to 31. Plus D, and then 11 minus 5 is equal to 6. And then, so we just simply solve for that. And this one's easy because it's just addition, no cube rooting or square rooting. So 49 minus 31 is 18. I definitely do not use the calculator for that. It's equal to D times 6. We don't have to put the parentheses, but I guess I'm doing it. Then just divide. So D, looks like D is equal to 3. Sorry if the words are in the way. D is equal to 3. So now we need to find the 25th term. So we plug in plug in N for 25. And then AK, we can use any of them. So let's go ahead and use 11. Because why not? Because we used the smaller one in example 2. So for example 3, we'll use the bigger one. So A11, then plus 3. Now we know it. Now 25 minus 11. That's going to give us 9. That's not going to give us 9. That's going to flip in and give us 14. So A25. And then we can replace A11, which is 49. Plus 3. That's 14. So minus 49. Oh, shoot. So now just do this into the calculator. So 49 plus 3 times 14. That gives us 91. So A25 is equal to 91. But if we did the other way and put 5 in there, so let's try that real quick. A25 is equal to A5. Then we'll put 31 plus 3, 25 minus 5, that gives us 10. So 31 plus 3 is 10. Bruh. And then if we put that into the calculator, 31 plus 3 times 10. My bad, this is not 10, this is 20. What's going on with my subtraction today? That's crazy. So 31. Actually, let's go back and look at this right here. So we have that up there, the one using the 11th term. So now doing the 5th term, they should both result in the same thing. And they do. A25 is equal to 91. So when we look back at the equation, it's saying determine how many seats there are in the 25th row. So we know it's 91 seats. 91 seats. Alright, and that is topic 2.2 of APP Calculus. And I hope that helped you. Thank you for watching.